You guys enjoy the snow? No? How did it go out? The roads were still travelable, so I was fine with it. Did you go out in the snow and do anything? No? Do you have a PowerPoint for today? I guess I'll follow it somewhat. But I'll leave the video up too, so I don't know what to do. So I put a couple more things on D2L for quizzes. One on mole fraction and one on molality. I want to get more up there that's more like the rest of the examples I did last time. I'm just not up yet. So study the examples I gave you last time for any of that you want to go over. And I'm going to move on to reaction rates, which is the next chapter, for really kinetics in general. When you took this in high school, did you do kinetics? Let me ask you this. How many of you guys have taken calculus class? How many of you have not taken calculus? Okay. I wasn't sure it was a prerequisite in this class. There's a calculus way to look at this, but we won't do it. If you have this reaction, something that you probably didn't talk about at all in high school, and we certainly haven't talked about yet, and you didn't talk about last semester, is reaction rates. In fact, I'll bet time barely came up at all. So now we're going to talk about how quickly a reaction goes. If you have a reaction like this, the rate, I won't say like this, the rate equals, for this one, it would be 1/2 delta t. So that's going to be seconds. This 2 comes from here, so I'm putting it on the bottom here. I'm putting a negative here because this is disappearing and these things are appearing. That is necessarily equal to not a negative value, but a positive value. There's nothing there, but I'm going to do a 1/1 just to keep everything consistent. Change n into that's necessarily equal to 1/3 delta. I know it looks a bit abstract, but that's just a general rule. That's the first thing I have on my PowerPoint up there. Really the most abstract way to put it is the way I've got it on the top right there. But as an example, there's this. But just to disambiguate a little bit, the units here, let me just repeat this one. There's no units that goes with that. This literally means the brackets just mean concentration. Have you seen that bracket notation before? It comes up a lot in kinetics. You've seen it before, you probably did kinetics, or did you do molarity that way? I thought you noted, huh?
Molarity.
Okay. Well, this is going to be in molarity. This is literally the molarity. It's change in molarity. Get to that in a second. So this is moles per liter on top. So that's this concentration here, moles per liter. What I would usually write this is I'll just leave the bracket. So in parentheses there is the unit, and down here it's just seconds. But notice it's change in. You ran into a delta T last semester. This semester the delta comes from, let's go to my next slide. Slide 2. This will just give you an example. Is that the one I've got there? No. So here's an example of a question you could get. This is still very simple, so don't let the abstract nature of it throw you off. You have that. You're being asked for. I did upload that if you want to bring it up on a computer. Relate the rates of consumption and the reaction rates of formation. These are being consumed or reacted. These are forming or appearing. This book uses all kinds of different words, but this is disappearing, this is appearing. And it's just this. It's literally a copy of what I've got there, except for I'm doing this. Over delta T, that equals, and this is negative because this is going away, so the rate is, the concentration is decreasing. So despite the fact that this looks a bit abstract, don't get lost here. I'll show you what you do with this in just a second. T equals, now it can be positive 1 over 4. T equals positive 1 over 6. Delta concentration of H2O and molarity, delta T. Okay. But I want to get to So I'm going to go to slide 3. I've got a couple of examples here. And I'll flesh this out with this example. I'm just trying to get to this example. You're given this as the reaction. The reaction takes place, specifically this is a dimerization reaction, but that really doesn't matter. All you really need to look at is this, and then you've got data in a chart here. Concentration in molarity, that's like the header. And then you've got so at 0 seconds, that's saying at 0 seconds, this is the concentration of the C4H6. And then at 1600, 3200, 4800, 6200. I wish I could project onto this screen. 5.04 times 10 to the negative 3. 3.37 times 10 to the negative 3. And then negative 3. And what you're asked for here is what is the average rate? 0 and 1600 seconds. It also asks you for just kind of as a second calculation. But this is where these deltas come up. So you could, right now, write down the rate as, use the same nomenclature. Rate equals minus 1 over 2, back to delta concentration of C4H6, delta T. Delta is always final minus initial. So if I'm going from 0 to 1600, and my final is 1600 and my initial is 0. So down here for the delta T, 1600 seconds minus 0.
Why does it go in increments of 1600 and they go to 6200?
You start at 0, you get up to 1600 seconds, and this is the concentration. When you get up to 3200 seconds, that's the new concentration. Then you get to 4800, that's the new concentration. And then you get to 6200, and that's the new concentration.
So it just happens to be 62. It's not. That's just how it is.
6200. This is just data collected from a reaction.
Okay.
This I'll always give you. In a chart like this, I'll give you these two. We didn't predict this. Yeah, I'm just using it here.
I'm just curious why.
Why do you put 1600 seconds minus 0 not plugged in for delta T?
For this,
Under C4.
this right here.
Yeah.
We're asked for what is the average rate for this reaction between 0 and 1600 seconds. My final is 1600, my initial is 0. So I do final minus initial.
Do you plug that into under C4H6?
Sorry, say again.
Could you plug it into the first fraction, like delta C4H6 over delta T? Could you just plug in 1600?
Yeah, I'm just being formal. Yeah, that's going to be 1600, yes. Because the second question says 16 to 32, and then I'd have 3200 minus 16. And then this would be non-trivial. But yeah, I'm just being formal by putting a 0 there. Make sure you always do final minus initial. And then final minus initial here is these two. This is final. That minus. And that'll give me my answer. It's going to be moles per liter per second. So my delta concentration is final minus initial minus my initial. My delta T is final minus initial, final minus initial. You guys follow me? And the rest is just plug and chug. What's that 1.0? Confused. You got to pay attention to the powers of 10. That is just to make sure I don't mess up. Which is 1, 2, 3. That over 6,800. This is moles per liter, and this is seconds. Oh, 5.